Hello, I'm Officer Cadet Martinez Chung, and in this lesson we will cover atmospheric pressure and density. Alright, first let's start with a Mercury Barometer. So, what a Mercury Barometer is an instrument we use to measure atmospheric pressure. So, atmospheric pressure is caused due to essentially the air. Okay? So the atmosphere actually has weight. And you don't really feel it much right now, and we will go over how that actually works, but it has weight. And that weight inside this apparatus actually pushes on the mercury that's inside, it pushes it down on the bowl, and a part of that mercury actually goes up into the tube. And that usually gives us a pressure reading. In this case, 29.92 inches of mercury. That's like the length of how much mercury is in the tube. Right? The reason we can actually get this is because the tube is actually a vacuum. There's nothing keeping the mercury down or keeping it out of the tube. So, yeah. Units of measure. Alright, so pressure is a measure of force per unit of area. So, as we discussed before, the air around us has weight. And we measure that using pascals. It's the unit of measure for newtons per meter squared. In order to give you an idea of how much pressure is actually on top of us, think about it this way. So, you have a table and there's a piece of paper on it. Right? Just a regular piece of paper. That piece of paper right now is currently applying about 1 pascal of pressure on the table. Just around, just a little bit less than that, but yeah. So that's 1 pascal. Now, the actual average atmospheric pressure of the atmosphere is 101.325 kilopascals. So, roughly 100,000 pascals. So you think about it, right now you have the weight of 100,000 pieces of paper right on top of you. That's all the air that's right on top of you. It's a lot. But how come we don't feel it? Well, the reason being is because our bodies also exert pressure. So all the liquids and gases and everything in our bodies is actually exerting pressure outwards. So that actually counteracts the pressure created by the atmosphere, which is why we can move around freely without feeling the actual weight of the atmosphere. Our bodies have just evolved and adapted that way. This is also one of the reasons why if you go into outer space without a spacesuit, then you will start to expand because of all the pressure inside of you that's kind of pushing you out. Now don't worry, you will actually not pop just because your skin has enough elasticity to keep you in one piece. However, I still would not recommend it. Anyways, back to units. So, we discussed pressure, inches of mercury, as we saw the Mercury Barometer in the previous slide. Then we measured how much mercury is inside of that column, and that's our inches of mercury. Next we have a millibar. So the millibar is the pressure exerted on an area of 1 square centimeters by a force of 1,000 dynes. So you don't really need to know or remember the dynes unit. We don't really use it much. But the millibars we do use. And what's actually more helpful is 1 millibar is actually equal to 1 hectopascal. Okay? So hectopascal being, let's say 100,000 pascals would equal about 1,000 hectopascals, essentially. Alright, ICAO International Atmosphere. So this is a very important thing you should remember, especially for exams. So, ICAO is the International Civil Aviation Organization. So it kind of like regulates aviation all throughout the world, civil aviation anyways. So in order to actually have like a standard for manufacturing and performance and stuff like that, then ICAO says that the atmosphere is standard, has these settings essentially. So first of all we have, for example, mean sea level pressure. So The pressure at sea level, according to the ICAO standard atmosphere, is 29.92 inches of mercury, or 1013.2 millibars, or hectopascals, or 101.32 kilopascals. Another thing it states is the mean sea level temperature, which is 15 degrees Celsius. Next, they also state that air is a perfectly dry gas, which, like, what? That doesn't make sense. Then how do we get clouds, right? But again, this is just a standard to which we base our manufacturing and performance. So, yeah, it doesn't really have to make sense. And finally, we have the lapse rate. So what a lapse rate is a change of temperature with a change in altitude. So in this case, the standard lapse rate is 1.98 degrees Celsius per 1,000 feet. So every time you climb around 1,000 feet, the temperature will drop by 1.98 degrees Celsius when compared to the ground. Density. Right. So what density is a measure of mass per unit of volume. Mass is how much stuff there is, essentially, like how much stuff there is in you. It can usually be related to weight, but in this case not as much. There's a couple of differences that don't really apply. Volume is how much space you occupy. So for example, something that's really light, like let's say foam, has a very low density because there's a certain amount of mass. However, it is divided along a lot of volume, so it has a low density. On the other hand, there's things like black holes, for example. That's the really extreme. Black holes are extremely dense. So think, for example, the mass of the Earth. Right? The Earth is very big, right? If you take that much mass and shrink it into something about this size, then you get a black hole. Think about it. The weight of the Earth is in a ball around this size. It's a lot. Next up is pressure and density. So pressure and density are directly proportional. So as we have more density, so more mass per volume, then we also have more pressure. This is because as we have more density, you usually have more molecules bumping around in a set volume. And those molecules bumping around, that's what actually creates pressure. So you think of a gas inside of a container, and the air molecules kind of bouncing around the sides of it. That bouncing around the sides is the pressure. Alright, next up we have what we call an altimeter setting. So, an altimeter setting is used to adjust the altimeter for variation in atmospheric pressure, right? So the thing about the atmosphere is pressure is not constant everywhere. There's areas of high pressure over here, there might be areas of low pressure over there. You can imagine me with like a weather chart, kind of like charting stuff. So kind of like in a news broadcast. So that means we have to adapt our altimeter to whatever pressure we are at right now, essentially. And that's why we have the altimeter setting. It's kind of like a little dial right next to the altimeter, and it sets your altimeter to what the current pressure is, and that will be your ground level. And this measure is usually measured in inches of mercury. That's just the common unit that's used here. Alright, now, meteorological aspects of the altimeter. So the thing about the altimeter is that it's susceptible to pressure errors. Now let's say, just like in this scenario, we're flying from an area of high pressure to an area of low pressure. However, for the altimeter, then even though we maintain our altitude relative to the ground, the altimeter detected a decrease in pressure. Therefore, the altimeter now thinks that we've actually climbed. And in order to correct, what we as pilots would do in order to maintain our altitude is we would pitch down in order to maintain altitude, even though we're already maintaining altitude. And thus, we end up closer to the ground. So here's the saying that you should remember. High to low, look out below. So this means when we're going from an area of high pressure to an area of low pressure, then your altimeter will tend to read higher than you actually are. And this will result in you actually flying too low to the ground especially. So look out below. And then the opposite also happens. So let's say we're going from an area of low pressure to an area of high pressure. Alright, so again, if we're flying straight and level, not changing our altitude, the altimeter will detect an increase in pressure. And so the altimeter will start to read a lower altitude than it actually is. And us as pilots, we would correct by climbing. So, and in the end, we're actually going to end up higher than we actually are. And that's why we also have a saying here. Low to high, clear blue sky. So when we're going from an area of low pressure to an area of high pressure, then chances are you're going to end up higher than you think you are. Right out on the clear blue sky. Alright, that is all. So if you have any questions, comments, concerns, queries, or random outbursts, feel free to put them in the comment section down below. Thanks for watching, and happy landings!